Hey guys, today we're going to begin our discussion on solutions. Okay, first thing we need to talk about are types of mixtures. Our first type is heterogeneous. This is non-uniform mixture composition. That means you can see the different parts. And I think I gave the example of black pebbles and white pebbles. If you had to, you could pick out all the black pebbles. We also have homogeneous mixtures. Those are uniform mixture composition. So you're not going to be able to see the different parts. And that would be like sugar water. You couldn't pick out the sugar molecules from the water molecules. Homogeneous mixtures, that's a uniform mixture composition, and that means you're not going to be able to see the different parts. They're going to look the same. Okay, so we have a lot of vocabulary in this particular section, and unfortunately they all sound a lot alike. You're going to have soluble, solution, solute, solvent, so make sure that you're studying. Now, soluble means capable of being dissolved. An example would be something like sugar cubes in water. Eventually, all the sugar molecules become uniformly distributed among the water molecules. A solution is a type of homogeneous mixture, and it's two or more substances in a single phase. The way it's classified is it has very tiny particles. The particle size is less than 1 nanometer. And if you'll remember, that's 1 times 10 to the negative 9 meters. We're talking something really small there. Every solution has 2 parts. Our first part is our solvent, and that is the substance. That's what SUV stands for, substance, doing the dissolving. And we also have our solute, and that is the substance being dissolved. So if we think about our sugar water example, sugar would be the solute, and water would be the solvent. And water is a pretty popular solvent. Most of the time we only think of solutions as a solid dissolved in water or some other liquid, but we actually have different types. We have a gas-gas solution, and that would be something like the air around us in this room. You can have a gas-liquid solution, and that's going to be like soda. When you open it up, you see the carbon dioxide come out of solution. We also have gas-solid. I guess that would be something like a marshmallow. Liquid-liquid, so 2 things that could dissolve in one another. Food coloring and water. Liquid, solid, and we talked about that as far as dissolving a solid in liquid. A solid-solid solution is something that we call an alloy. It's something that some of you may actually be wearing right now. 14-karat gold jewelry is an example of an alloy. Basically, gold is too soft to be used in jewelry because it just scratches, it bends. But if we alloy it with silver or mix it with silver, we increase the hardness and the strength of that particular product while still maintaining that gold look. A suspension is a type of heterogeneous mixture. It has large particles that settle out unless stirred. The particles are really huge, and so those are going to be over 1,000 nanometers. And it's basically just too heavy for the solvent to hold, and so they settle out over time. The classic example for this is muddy pond water. Muddy pond water looks like a solution, and then you let it sit, and all the mud falls to the bottom of the solution. A colloid is another type of heterogeneous mixture. A colloid has intermediate sized particles, so somewhere in between a solution and suspension. It's between 1 nanometer and 1,000 nanometers. One of the distinguishing characteristics of a colloid is that colloids exhibit the Tyndall effect. This occurs when light is scattered by those medium-sized particles. This picture shows how colloids exhibit the Tyndall effect. The red solution is a colloidal solution, and so you can see the light as it passes through the solution scatters, and so it kind of looks fuzzy. You can see that beam of light. Whereas the yellow solution, which is a true solution, they have those really small particles, and the particles are too small to scatter any light. If you've ever driven through fog, you will have seen the Tyndall effect. When you drive through fog, if you have your lights on high beams, then there's too much light scattered and you blind yourself. So you have to drive with low beams on so that there's not too much light to be scattered by the fog, which is also a colloid.
This is a pretty good summary. There are a few little things that are mistaken. This is taken out of a physical science book, but these should be right here around 1,000 nanometers instead of 200. One of the things that I didn't address before was, can we separate them using filter paper? Solution and colloids, the particles are still too small. They'll go right through the filter paper. But suspensions, we can filter out those.
We have two classifications of solutes, electrolytes and non-electrolytes. Now, we've discussed this before. Ionic compounds and certain highly polar molecules are considered electrolytes. The ionic compounds split into their ions, and so there are these charged pieces that are able to carry an electrical current, which makes them electrolytes. There are three factors that affect the rate at which a solid solute dissolves in a liquid solvent. Here we're talking about something like dissolving sugar in water. If you know how to make sweet tea, you already know these three factors. So my first question is, do you use sugar crystals or sugar cubes when you make tea? You're going to use your sugar crystals. And the reason for that is because it has a higher surface area than a cube. If you think about it this way, a cube of sugar, the only sugar that's coming in contact with the tea is going to be those on the surface of the cube. All of those in the middle of the cube are trapped inside, and so they're not going to dissolve until the actual tea gets to them. Here's my second question. When you're making tea, do you just have the tea, dump the sugar in, add some water? No, you actually are going to end up stirring it so that the sugar dissolves. So stirring a solution is going to increase the rate at which it dissolves. Okay, last question. When you're making tea, do you let the tea cool down before you add the sugar, or do you add the sugar while it's still hot? You add it while it's still hot, because heating a solvent is going to increase the rate at which it dissolves. The heat helps separate those molecules, and you kind of have your own little molecular mixer because those molecules are moving faster at a higher temperature. There is a limit to the amount of solute that can be dissolved. You may have tried this as a kid, where you're trying to put sugar in Kool-Aid or something like that, and you put a little bit of sugar. It's good, but so how about a whole lot? Well, eventually what happens is the sugar that you try and put in there ends up just going straight to the bottom of the container, and you can stir all you want. It's not going to go into solution. Well, at that point, you have reached solubility. That is what that limit is called. Now, we have lists of solubilities of lots of different compounds, and they're determined experimentally. Now, they have kind of strange units. It's grams of solute, so how much can dissolve in 100 grams of solvent, and that solvent is usually water. The next term we need to look at is the term saturated. I think it's easier to think about it if you think about a paper towel. If it is thoroughly saturated with water, that means it can't hold any more water. Well, a saturated solution is a solution that cannot hold any more solute. If you add any more, that solid is going to go straight to the bottom and will not dissolve. So that's a saturated solution. Now, an unsaturated solution is one that can hold more. This would be like a dry paper towel. You can put more water on that. Now, when I say that in a saturated solution, if you add more solute, it's going to sink right to the bottom. Well, and that does happen, but it's not just going to sit there this entire time. It's going to be a little more dynamic than that. You've got crystals that are solids are going to dissolve and go into the liquid solvent and mix together. While that happens, the solution cannot hold any more of that solute. So others will crystallize out and be solid on the bottom of the container. So it sets up this equilibrium, and so you have those crystallization and things going into solution happening at equal rates. A supersaturated solution is one that holds more solute than it should at a particular temperature. And so we do that kind of by tricking the solution. We heat it up and dissolve more.
Flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added.
A supersaturated solution is,
And what you just saw there, sodium acetate, that supersaturated solution, when they put a seed crystal in there, now it could have been a string, but this time it was a seed crystal, it caused mass crystallization and the entire thing turned into a solid. And that is generally what will happen with a supersaturated solution once it's been disturbed.
okay, here we have a solubility curve for a lot of solids and gases in solution. And if we want to know the solubility of a particular solute at a particular temperature, we're going to need to be able to read this graph. So the example I have set up here is if I want to know the solubility of potassium chlorate, I've got to find potassium chlorate curve on the line. And let's say I want to know the solubility at 50 degrees C. I go to the temperature scale, find 50, go up, and find where that meets the curve for potassium chlorate. And then you go over and look at its solubility. So it is 21 grams of solute will fit into 100 grams of water. So pay attention to those units on solubility because they can be a little tricky. Using your copy of the solubility curves, I'd like for you to answer the following problems. Jot the answer down on your paper and we'll discuss the answers here in a few minutes. The answer to this one is 206 grams of sodium nitrate will need to be dissolved in 200 grams of water. And that was the key there. They ask about 200 grams of water, so you have to pay attention to those units on solubility. They are a little strange. So when you read the graph, it says around 103 grams will dissolve in 100 grams. So double that would dissolve in 200 grams. The answer to problem 2 is approximately 77 grams of potassium nitrate will precipitate out of the solution. What you have to do to answer this problem correctly is you have to remember that solubility is that maximum amount that can be dissolved in a solution, that saturated solution. So you look at both temperatures. At 60 degrees C, the maximum amount that can be dissolved is 110 grams per 100 grams of solvent. At 20 degrees, the solubility is only 33 grams per 100 grams of solvent. So as that thing is cooled down, whatever will not fit that's below its solubility will fall out and become a precipitate. So you look at those two solubilities and you subtract the two.
Okay, when we're talking about solutions, we will also talk about concentrations. Now, we have worked a lot with molarity, and that is with the big M, molarity. It's moles of solute over liters of solution. One that we haven't worked with too much, at least this far this semester, is molality. And it's usually a lowercase m, and it kind of looks a little italicized or fancy. And it's moles of solute over kilograms of solvent. When you're working with molality, it is very important, and it just makes the problems easier. If you go ahead and identify which one is your solute and which one is your solvent. Be very conscious of what units these things are in. Solvent has to be in kilograms. The solute has to be in moles. Now, you can use the triangle trick. We've used that quite a bit. Molality equals moles of solute over kilograms solvent. And that can help you out with those really quick rearranging of the equation. Okay, to work a very basic molality problem, we have 13 grams of NaCl is dissolved in 500 grams of water. This is my solute, and this is my solvent. Like I said earlier, water is a very popular solvent. Usually if it is present, it is going to be your solvent. So, we need our solute in moles. So we're going to take our 13 grams of NaCl, and we are going to convert that into moles. So there are 58.44 grams in 1 mole of NaCl. So here we're going to end up with 13 divided by 58.44. 0.222. Again, remembering those sig figs, that's our moles of solute. Then we're going to have to divide by our kilograms of solvent. They gave me the grams. I'm going to go ahead and convert that to kilograms. So it's 0.5 kilograms. So my moles divided by my kilograms of solvent is going to give me my molality. And you should get 0.444 molal. These types of calculations are going to be pretty important, especially if we get into freezing point depression and boiling point elevation. The concentration that we deal with there is exclusively molality, and it does serve a very important purpose there. Now, these other types of problems are just rearranging the equation, how many grams of magnesium chloride are needed to make a 3.5 molal solution in 450 milliliters of water. Well, MgCl2 is going to be my solute, and water is, again, going to be my solvent. I know I need my solvent in kilograms. It's water. The density of water is 1 gram per milliliter. So 450 milliliters is 450 grams. And that I need in kilograms. So we'll move that decimal over 3 places. 0.450 kilograms is my solvent. They also give me my molality. I'm actually looking for my solute. So moles of solute, if I rearrange the equation, is going to be equal to molality times my kilogram solvent. So it's 3.50 molal times my 0.450 kilograms of my water. And that's going to give me moles. Like I said, you need to be very cautious and conscious about the units that we're using here. And I got 1.58. We'll keep it to 3 sig figs. And that's coming out in moles of my solute. But it asks for grams. So I need to convert moles to grams. In 1 mole of magnesium chloride, there are 24.31 plus, and I get 95.21 grams. And I get 150 grams of magnesium chloride need to be dissolved. This last one here is just another rearranging of the equation, except this time you're looking for your solvent, and it's asking for it in milliliters. So again, you'll have to deal with the density, and in a lot of the problems that we'll be looking at later, the density is going to play a much, much bigger role.